Hey all, here we are on 9.6, which is our last section in the convergence and divergence tests. If you've understood what we've done so far, you're doing amazing. This stuff is so hard at first. I remember learning this my first time and it was very overwhelming. So we have two more tests to learn today, and then we're going to try to kind of come up with a generalized strategy for how to do this. All right, so the first thing we're learning, first new test we're learning is called the ratio test. I need you to go ahead and cross something out here. We don't need these summation things on the inside. We're only testing the nth term in the a to the n plus 1 term. Basically what we're doing is we can tell that it converges absolutely if the limit as n goes infinity of the absolute value of the a n plus 1 term divided by the a nth term is less than 1. So remember, this is just you replace the n with n plus 1. It's basically the next term. Basically, we need to show that the next term divided by the current term is always less than 1. That means it will converge. If we can show that that limit is greater than 1, then it will diverge. And if it equals 1, then it's inconclusive and we have to do something else. All right, so let's give this a shot, right? In this case, again, like we should always do that nth term test just to make sure that it doesn't diverge, right? So let's just do that real quick, right? What's the limit as n goes infinity of 2 to the n over n factorial? If you remember, factorial is the only thing that grows faster than 2 to the n, so this actually goes to 0, right? So we're going to define two things. We're going to define a to the n, which is, again, just that same thing, and we're going to define a to the n plus 1, which is, we can do this one in green, which is the same thing except we're replacing n with n plus 1. So that looks like this. And what we're going to do is we're going to write the limit as n goes to infinity of the absolute value. Remember, all the absolute value is going to do is take away like one of those negative 1 to the n power or n plus 1 power, something like that. And we're going to put the n plus 1 term on the top, right? So 2 to the n plus 1 over n plus 1 factorial. And this is going to be divided by 2 to the n over n factorial. And basically we're trying to show that this is less than 1. Well, we're trying to see what happens, right? So let's just do it. Limit as n goes to infinity. Let's see. So to rewrite this, 2 to the n plus 1 is the same as 2 to the n times 2. Right, this is the property of exponential functions. It's like 2 to the n times 2 to the 1. You can add those exponents. And then n plus 1 factorial can be written as n plus 1 times n factorial. A helpful way to think about this is if I have 9 factorial, that's the same as 9 times 8 factorial. Right, so like an n plus 1 is always like the higher one, right? So 9 times 8 factorial. If I had 15 factorial, that's the same as 15 times 14 factorial. Okay, so I'm going to need to use these two things down here, right? So there are no negative terms, so we can kind of just get rid of our absolute value symbols. The numerator here is going to become 2 to the n times 2 divided by n plus 1 times n factorial. And then instead of dividing by this fraction, we're going to multiply by the reciprocal. So this is that an term, right? And that will always happen. So in the future, instead of like writing the division, I'm going to go ahead and write the reciprocal just to make life easier. And then this n factorial cancels with this n factorial, and this 2 to the n cancels with that 2 to the n. And we're left with the limit as n goes to infinity of 2 over n plus 1. Which this is going to go to 0, right, which is less than 1, and so this converges. So the series converges, right, because 0 is less than 1. Okay, let's try another one. Number letter B here. Again, let's just do a quick the nth term test. If I go n goes to infinity, then I have 3 to the n is going to grow faster, right? And this is going to go to 0 because 3 to the n grows faster than 2 to the n, and 4 to the n grows faster than that. And the n squared there doesn't really do much for any in the long run. So let's do our test. We're going to take the limit as n goes to infinity of the absolute value of a to the n plus 1. So that's when I plug in n plus 1 here, that's going to become n plus 1 plus 1, which is n plus 2, and then divided by 3 to the n. And like I said before, I know that I'm going to have to divide by, I forgot the plus 1 here, plus 1. I have to divide by this thing, which is the same as multiplying by the reciprocal. So instead of writing all that out, we're going to go to multiply by the reciprocal. Like such. And then we need to rewrite the n plus 1 term. Again, there's no negatives here, so I can get rid of the absolute value. This is still going to be n plus 1 squared. The 2 to the n plus 2 is going to end up being, we want it to cancel with 2 to the n plus 1. Well, let's just write it like this. 2 to the n times 2 squared. And then the bottom is going to be 3 to the n times 3. And we're multiplying this by 3 to the n squared, and then 2 to the n times 2. I'm going to go and rewrite that using that property exponents. And then what cancels? Well, 2 to the n cancels 2 to the n, 3 to the n cancels 3 to the n, and we're left with limit as n goes to infinity of, it's going to end up being n plus 1 squared times 4 over 3n squared times 2, which ends up being 6. And we're taking the limit as n goes to infinity. We could go to multiply out this top, right? It's going to be 4n squared plus 8n plus 4. Right, just foiled that thing and then multiplied by 4. And then we're still taking the limit. We still need the limit here as n goes to infinity. We can use an n behavior model. This is going to approach, those cancel 2/3, right? That's 4/6, which is 2/3, which is less than 1. So the series converges. All right, next one. N to the n over n factorial. This is a weird guy. Now, we know that like n to the 5th power grows slower than n factorial. And we all notice that 5 to the n grows slower than n factorial. But do we know that n to the n, how does that grow compared to n factorial? Well, or maybe we're not sure at this point, right? So we're not really sure what the nth term test would give us there. So let's do our ratio test, right? We're going to do absolute value of n plus 1 to the n plus 1 divided by n plus 1 factorial times, remember, instead of dividing by this, we're going to multiply by the reciprocal because it's a fraction. So we'll multiply by that. And then we need to do some simplification that's going to allow us to evaluate this. Again, there's no negative, so just ignore those absolute value symbols. This is going to be n plus 1 to the, let's go and leave it as n plus 1 over n plus 1 times n factorial. Again, I'm using this trick up here that we did up here, times n factorial over n to the n. I'm trying to think here if I should have simplified this a little bit. Maybe not. So what cancels? Well, the factorials cancel in this case. And yeah, you know what? I think I need to rewrite. But let's go ahead and take it from here, right? So this is, I'm going to go ahead and rewrite this guy. So this is going to be n plus 1 to the n times n plus 1 to the 1, and then times, now it's 1 over n to the n. And what that does is allows these two to cancel. And so we have a limit as n goes to infinity of n plus 1 to the n over n to the n. Notice how they have the same exponent, right? This one's going to take a little bit more algebra to do. We could write this as, since they both have the same exponent, we could write it as one single number to the exponent, which could also be written as, simplify this fraction, right? N over n is 1 plus 1 over n to the n. And hopefully you're starting to recognize this guy every time it appears. They love just throwing it in there. This is actually the definition of E, which is greater than 1, right? It's 2.71 something. So this series diverges, right? Ratio test shows that it diverges. All right, next one. Do the nth term test real quick on this. Square root of n over n plus 1. Which one grows faster? Well, square root of n is like n to the 1/2, and that's like n to the 1. So the bottom grows faster and it goes to 0, right? So we can't just quickly get out of this one. So we actually need to write it out. Limit as n goes to infinity, absolute value of -1 to the n, square root of n plus 1 over n plus 1 plus 1, right? We're adding 1. And then we're going to divide by this whole thing, which is the same as multiplying by the reciprocal. So it's going to be n plus 1 over -1 to the n, square root of n. And this is one of those cases where the absolute values actually help us out, right? Like all these -1 to the n powers do is either make it positive or negative. And so the absolute value is just going to take that away, right? It's going to say, well, it can't ever be negative. So we're going to be left with square root of n plus 1 over n plus 2 times n plus 1 over square root of n. And now we got to evaluate this one. So in order to do this, we need to rearrange a little bit. And we're going to write square root of n plus 1 here. We're going to write this square root of n over here, right? So notice how I just basically swapped the places of those two things, which is multiplication, so we're allowed to do that. You know, the order in which you multiply doesn't matter. This one can then be written as n plus 1 over n, and this one is n plus 1 over n plus 2. Now we can take the limit of each of these pieces individually, right? If I take the limit of this piece, it's going to go to, you know, as n goes to infinity, this is going to go to basically square root of 1, right? N over n is 1, and then this guy is also going to go to 1 as n goes to infinity. And so I have square root of 1 times 1, which is 1. And so in this case, the ratio test fails, right? It's inconclusive. And what I could do is try a different test, which this is an alternating series. So I could try an alternating series test. Let's do that. Let's just real quickly do it. First we need to show the limit as n goes to infinity of square root of n over n plus 1 goes to 0, which it does, like we talked about in the beginning. And next is I need to show that it's an plus 1 is less than an. Basically, another word for this is that it's decreasing. So an easier way to show this, that's actually really formal, is to define the function, right, and then take the derivative, which I'm not going to go through this whole thing with you, but if you took the derivative of this, you would get negative x plus 1 over 2 square root of x times x plus 1 squared. And we can show that this, for n greater than 1, this is always negative, right? This bottom part is always positive, and then for x greater than 1, it'll either be 0 or negative. So you're going to have either the answer of 0 for the first term, which is fine, and then it's going to be negative, meaning it's always decreasing. And so we basically, because it's decreasing, that must be true, right? The next term must always be less than the one right before it. So we can show that by the alternating series test, it converges. All right, so that's that one. Let's go on to the next test, which is the root test, the nth root test. Basically, in this one, what we're going to do is we're going to take the nth root of the absolute value of the nth term. And same idea, if it's less than 1, it converges. If that nth root is greater than 1, it diverges. And if it equals 1, then, well, you're stuck, right? And you got to do something else. So, here we are. What we're going to do is we're going to, first check. It's a little bit hard to check. We don't know how n to the n grows, but n to the n is definitely going to go faster than e to the n, right? So this does, the nth term test goes to 0, so it doesn't diverge, or we don't know that it diverges yet. What we need to do is we need to take the limit as n goes to infinity of the nth root of the absolute value of the thing, of our little explicit formula there, right? So we're taking that. And there's no negatives here, so this can just go to, right, we can just kind of ignore those absolute value symbols. And maybe it's helpful to write it as a fractional exponent, right? Remember that the third root of x is the same as x to the 1/3. The 10th root of x is the same as x to the 1/10. So the nth root of x is the same as x to the 1 over n, right? So this is going to become e to the 2n over n to the n raised to the, let me do this in a different color, 1 over n power. And properties of exponents say that this 1 over n distributes in there and gets multiplied. So this is going to become limit as n goes to infinity of e to the 2n over over n divided by n to the n over n, right? What we did is we took this guy, multiplied it in there and there. And then we simplify. Let's come down here. Limit as n goes to infinity. That's e squared over n. And this is going to go, this is a constant, over infinity, which goes to 0, right? Which 0 is less than 1. So by the nth term test, the series converges. All right, so those are all the tests that we're going to learn. Now let's talk about some strategies. First thing you should always do is the nth term test for divergence, right? Because if you can show that it diverges with that test, then it definitely diverges. The next one you want to look at is it a special kind? Is it a p-series, a geometric series? Is it telescoping, or is it alternating? Right? Those are the 4 easiest ones to show convergence for. If none of those work, or if it's not any of those, then you want to look at the integral test, see if it's easily integrable. The root test, which we just did, or the ratio test, which we just did, right? Those ones are pretty straightforward and easy. And then if none of those work, then you can try to use one of the comparison tests, right? Like limit comparison test or direct comparison test. And those ones are a little bit more advanced to apply, but they still work. All right, so let's apply some of these to these problems here, right? First thing is we always try is the nth term test, right? So we just try. In this case, we get 1/3, which is not 0, so this one diverges, right? That's that nth term test, that if you can show that it's not 0, then it diverges. Okay, next one, you'd say, okay, let me try the nth term test. Turns out that pi over 6 to the infinity equals 0, so the nth term test fails, but we should recognize this as geometric. It's a geometric series because it's in the form a r to the n, right? Some number to the nth power. Terms in this case, a is 1, r is pi over 6, and since pi over 6 is between, I can write here, between 0 and 1, the series converges. What does it converge to? Well, it converges to a over 1 minus r. So in this case, 1 over 1 minus pi over 6. But the important part is it converges. Okay, next one is n over e to the negative n. Nth term test, it's going to be, this is going to be n over e to the n squared. This does go to 0 as n goes to infinity. Sorry, let me write that a little bit nicer. The limit as n goes to infinity of an does go to 0, so that one fails. It's definitely not a geometric series. How do I know? Well, it's there's like an n squared up here, and there's like an n in here, which, it doesn't look like it. It kind of looks like a p series, except p series should be like 1 over, n to the 4th power. In this case, it's like n over e to the n squared, which is the variable for a p series should be the base of the exponent. In this case, the variable is not the base of the exponent, so it's not a p series. It's not alternating, it doesn't go between plus and minus, and it definitely doesn't look like it's telescoping, right? So let's try the integral test. Basically ask yourself, can I easily integrate that? And the answer is yes. If you let u be negative n squared, it integrates pretty easily. But remember, for the integral test to work, we need to show that it's positive, right? The terms are always positive, so yes, it will always be positive. If you're plugging in positives here, that'll be positive. This can never be negative, so it's positive. Is it continuous? Yes, it's continuous. There's nothing in the denominator that would make it 0. Even if you put e to the n squared on the bottom, you can never make that 0. Is it decreasing? You need to show that it's decreasing by taking the derivative. Which we could do that, and it will work in this case. So we can just integrate real quick. We're going to integrate from 1 to infinity n e to the negative n squared. Let's let u be negative n squared. Therefore, du is negative 2n dn, and dn is du over negative 2n. And so we're going to take the limit as a goes to infinity, 1 to a of n times e to the u times du over negative 2n. This will cancel, that'll cancel. Let me erase these guys. I'm going to go up here. So we're going to have limit as a goes to infinity of integral of e to the u is e to the u, and we're going to go ahead and plug in the n squared again, and there was this constant of negative 1/2 floating around, or negative 2 on the bottom, and we have to go from 1 to a. So basically this becomes limit as a goes to infinity of e, that's negative e over 2 to the negative a squared, minus negative e to the negative 1. This is going to become positive. A limit as a goes to infinity. In this case, this is negative 1 over 2e to the infinity, which is 0. And then so we're just left with e to the negative 1 over 2, which is that. So it converges, right? The limit exists. Therefore, the series converges to something less than this number here. Right, so we're going to say this guy converges by integral test. Okay, D. You can show that the nth term goes to 0 real quick. And then, but then, like, you know, it doesn't look like a P-series geometric telescoping or alternating, so we have to figure out something else. So what's nice about this one is it can be easily compared to 1 over n, and however you want to do it. Like, I think the limit comparison test is easier, just because you don't have to show that the next term's always smaller, or you know, you don't have to show that the terms in this guy is always smaller than the terms in that guy. The limit test, you just set up like a limit and then do it. Although these ones say root test or ratio test first, so why don't we just use a ratio test, because that's pretty easy, right? So we're going to put, alright, so we're going to put 1 over 3n plus 1 over 1 over 3 n plus 1. We're going to take the limit as n goes to infinity. There's no negative, so we don't have to worry about absolute values. Right, this is going to go to limit n goes to infinity, 1 over 3n plus 4 times n plus 1 over 1. And this is going to give us, basically, if you use your n behavior model, it's going to be 3n here and n there. So it's going to go to 1/3, which is less than 1, so it converges. Maybe it's easier to use direct comparison test with this guy and show that this guy diverges, and this must always be less than this one, because you're multiplying the denominator by 3 and adding 1, which will make you divide by a bigger number, and so it also diverges by the direct comparison test. But I feel like, you know, this ratio test is a little bit more straightforward on how to actually prove it. But anyway, let's keep going. Well, the lettering sucks on this, but we're on this one, which, because of this guy, looks like an alternating series test, right? Or an alternating series. So all we got to do is show that an, the limit as n goes to infinity of an goes to 0, and we got to show that an plus 1 is less than an, or basically it's decreasing the whole time. So if you look at this limit goes to 0, right? The limit as n goes to infinity of 3 over 4n plus 1 goes to 0, right? The denominator is bigger. And then show that the next term is always smaller than the other one. Let's just use the derivative. I feel like derivative is a surefire way to do this, right? So f prime is going to be 0 minus 4n plus 1 times 3 over 4n plus 1 squared, right? So this is, the denominator is always positive. The numerator for n greater than 1 is always negative, and so f prime of n is less than 0 for n greater than 1, right? So that means it passes the alternating series test. So by alternating series, it converges. You could also use a direct comparison, or you could use one of the ratio tests on that one as well. All right, f. We would try the nth term test for divergence, and right now we know that factorials grow faster, so this is actually big over small, which means the nth term test, right, the limit as n goes to infinity of n factorial over 10 to the n does not equal 0. Therefore, this series diverges. Maybe you're not confident about that. You want to do something else. You could try the ratio test. The reason we like ratio tests on this is because there's a factorial, and the ratio test does well with factorials. Right? So we're taking the limit as n goes to infinity. Again, we're kind of done already. I'm just trying to show you how, you know, you could use a different test. Sorry, we're supposed to be plugging in n plus 1, which is going to make this n plus 2 factorial. No, what am I doing? N plus 1 factorial. And then on the bottom we have 10n plus 1, and we're going to multiply that by 10 to the n over n factorial. A little bit of rewriting. This is going to be n plus 1 times n factorial over 10 to the n times 10, and then times 10 to the n over n factorial. and cancel, 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 cancel. So we're left with a limit as n goes to infinity of n plus 1 over 10, which turns out goes to infinity, which is greater than 1. So again, we can double check and say that it totally diverges, right? But we knew that in the beginning. All right, last one. Nth term test. You know, maybe this is when it gets hard to do the nth term test. Like, what happens is n goes to infinity. Well, you have basically the inside turns into 1/2 to the infinity power, which goes to 0, right? But maybe you don't, not even sure how to do that. So you might have to do some other test if you're not sure to do this one. And it's not geometric. It's not a p-series. You know, the ratio test could be applied, but imagine you have n plus 1 plus 1 over 2n plus 1 plus 1 and the n plus 1 in the numerator. It's going to get a little bit messy. The fact that there's like an n on the outside of this whole thing shows us that if we took the nth root, it would make life a lot easier. So let's do that. Let's take the limit as n goes to infinity of the nth root. Again, we're supposed to put absolute values, but there's nothing negative in there, to the n power. And basically what's going to happen is this nth root cancels out that n, and we're left with the limit as n goes to infinity of n plus 1 over 2n plus 1, which goes to 1/2, right? N behavior model, n over 2n, which is less than 0. So it converges, absolutely, right? All right, so that's all of them. Your practice set is here. Good luck on it. I will be printing out kind of like a summary sheet that goes over all the different ones. So look for that in the folder. All right, have a nice day.